Hi, Mark Radaelli from Italy. I'm going to tell you about the three wells potential problem. We are studying the quantum behavior of a particle in a three wells potential as illustrated, and we will discuss control strategies. That is, we will discuss what is the best way to tune the height of the barriers in order to transfer in the most efficient possible way the wave function from the well on the left to the well on the right. First, let us begin with a classical analogy for our system. If we represent the wave function with water, we are asking what the best strategy is of lowering and raising dams to bring in the quickest possible way water from the left to the right. However, quantum is not classical. When dealing with quantum features, we must take in account the tunneling effect. Quantum objects can pass potential barriers even if with low probability, as if there were tunnels excavated in the potential. Therefore, even if the barriers are raised, the wave function can slowly pass through them. In fact, also without any time modulation of the barrier's height, the wave function comes to the right well, as we can see in the simulation. First, I tried to manually tune the behavior of the barriers. The most natural way to do so is lowering the barriers to make the wave function pass, then raising it after its passage to avoid recoil effects. In this way, it is possible to transfer the wave function far more quickly than only letting it tunnel. The time dependence of this strategy I chose is shown in the graphs. However, as it often happens, manual tuning is not the best strategy. I tried to run the grape optimizer on this problem and got this strategy. As you can see, the grape formulated strategy has almost nothing to do with mine. Looking at the behavior of the wave function, we see that grape is able to exploit interference effects in the wave function, and this grants even better performances. Things get even worse when dealing with Gross-Pitayevsky dynamics. This is a nonlinear dynamical model widely used for a simple treatment of Bose-Einstein interacting condensate. The Gross-Pitayevsky dynamics follows an equation that is obtained from Schrödinger through the insertion of a nonlinear term with a coupling intensity constant beta. As a result, Gross-Pitayevsky dynamics appears to be far noisier than Schrödinger's. The noisy behavior is evident, for example, looking at these state evolution plots, where Schrödinger dynamics appear to give more regular figures. This fact also affects the control problem we are talking about. Manual tuning for Gross-Pitayevsky dynamics is almost impossible, and I only ran grape. It is apparent that the required strategy is more complicated, because of, as we said, a noisier behavior of the wave function. In the paper, I provided a brief analysis of the result presented in this video. Thank you for your attention.